Hello and welcome back to the IB Chemistry TZ2 May 2025 exam walkthrough. This is going to be paper 2, but now the HL version. If you haven't already, once again, I'm not going to go over the parts that are in common with SL. Like as you can see already in the screen here, is those parts are already filled in. So you can watch the videos there that have to do with that. The HL exam for paper 1B and 2 is just the SL version plus extra stuff. There might be a few marks that aren't in the HL version, just because I guess they considered it too basic. But anyways, one big difference before we even get into it is that if you swipe through the exam, is that normally the HL version is the SL version plus extra, like they expand some of the questions, but usually there's extra questions. Like it's normally like 4 for SL and then like 9 or something crazy like that for HL. And so this year they actually switched it up. I don't know if they'll continue to do this, if this will be the pattern for the 2025 curriculum. But they, rather than adding extra questions, they just fully expanded questions 1 through 4 for SLs. They kept the same number of questions, then just fully expanded all of them. Okay, and so these videos will be following the format of just the extra marks for each question that were added in. Okay, and so this one we're going to be starting off with this question number 1. This video will cover the subparts of A and B, just because there's a lot of extra subparts, so we don't want to make each video a million years long. And so starting off, we have this one of this part 2 that is new. You can see I have the parts that are new highlighted to say new. And so it is to deduce the hybridization of the carbon atom and the number of sigma and pi bonds that it forms. We covered this in the 1A videos, where hybridization is just based on the number of electron domains. There's sp3, sp2, and sp, and it's just literally the number. So for this one, our carbon, if we count our number of electron domains, we have 1 and then 2. So that means that our hybridization is going to be sp. Okay, because S and P, 1 plus 1 equals 2 domains. So SP. The number of sigma bonds in that carbon forms is carbon overall forms 4 bonds here. Okay, and so it forms one of the single bonds and one of these triple bonds. One single bond is going to be just 1 sigma. Okay, my screen share died. My bad. But so this is going to be just a single bond is 1 sigma bond. Meanwhile, we also have this 1 triple bond. And so 1 triple bond is going to be 2 pi and 1 sigma. And the way that I remember this is that single bonds, like all of the organic reactivity that we learn, is that single bond, like alkanes, are not reactive. That's because those strong sigma bonds are harder to break. Meanwhile, alkenes and alkynes are more reactive because they have those 2 bi bonds. They have 2 essentially easy pieces of armor to break through before you get to the strong sigma bond, if that makes any sense. So that's kind of how I tend to remember that. And so overall, you would have the number of sigma bonds would be 1 from the triple, 1 from the single, so 2 sigma, and then 2 pi in that triple bond. So 2 and 2. So that would be that 1A2 extra mark. And so moving on to the 1B3, this one is some math. The version of the SL version had just a simple pH calculation. Meanwhile, for the HL version, it gets more complicated because it is a weak acid. So it's going to be a weak acid pH calculation. And so it tells us that to calculate the pH, this is 0.1. It tells us the concentration, HCN. So I'm going to go ahead and just go, wow, concentration of HCN, and then it gives us the Ka of HCN. Every time you are given a Ka or a Kb value, you need to write out what the equation for that is, okay? Because it's going to help you know what the next steps you need to take are, okay? And so the Ka equation of HCN is, we already kind of wrote it up there, so we're going to just look at that again. Is that HCN, H plus, Cn minus, okay? And so our Ka, K is just our equilibrium constant, right? I mean, it is in the acids and bases unit, but it's a continuation because the weak acids are in an equilibrium. Okay, so it's the concentration of the products. So H plus Cn minus over the concentration of HCN. Okay, and so In this, we know the concentration of HCN. We're given that. We're given the Ka, and we need to find H plus. However, we don't know CN minus. And so this is when we have to remember the two big assumptions that we make whenever we're doing these weak acid slash base calculations. Is we always assume that the concentration of HCN initially is the same at equilibrium. So we use that value for our K equation. The other assumption that we make is that the concentration of H plus is the same as the concentration at Cn minus. So we can then rewrite this as being equal to H plus squared over HCN. Okay, and so once we've done that, we can now solve for this H plus. Okay, and so we can now rewrite this as just rearranging the equation. So to solve for H plus, so our H plus would be equal to the square root of the Ka times the concentration of HCN. Okay, and so if we plug in our values, that would be the square root of 4.9 times 10 to the negative 10, then times that 0.100. Okay, and so if you put that into your handy dandy calculator, you get roughly that H plus concentration is 7 times 10 to the negative 6 for our H plus. And so our pH is just going to be equal to the negative log of that, of our H plus. So that's going to be negative log of 7 times 10 to negative 6, which ends up getting us that 5.15, the same answer that we got in the HL version. However, the SL version. However, we had just a slightly different calculation because HL knows how to go more in depth for that. Okay. And so that was that BI. So that B4 is going to be to sketch the variation in the pH that would occur if you have 30 centimeters cubed of this 0.2 concentration of KOH. And so immediately the first thing that I'm noticing here, focus camera. It'll focus back at some point. I don't care. Is that our KOH is a group 1, or is it 2? 1. It's having a stroke. Group 1 hydroxide. And so that is going to be a strong base. And our HCN is a weak acid. Okay, and so our pH curves we always have is our volume of KOH. So we're adding KOH. So we're starting with HCN. So our first plateau is going to be around that, rather than like a really low pH. It's going to be in between, like around like 4 and 6. Okay, it's going to be around like that 4 and 6 kind of zone. And we're going to have our equivalent point. We need to calculate where our equivalent point is going to be in terms of the volume. However, our pH, we know from the combination of strong base and weak acid, okay, is because the pH at the equivalent point is based on the hydrolysis of the salt, okay? And so whenever you have this HCN reacting with this KOH, is they are going to form this KCN salt plus just water. And so that's going to undergo hydrolysis. And so there's two options for you have to see the cation and the anion, whether or not it will undergo hydrolysis. And so for your CN minus, your anion with water, is if it did undergo hydrolysis, which all of these hydrolyses are going to be equilibriums, is it would form this HCN plus OH minus. HCN is a weak acid, and so therefore this reaction will occur. Meanwhile, our cation, so our K plus, if it reacted with water in a hydrolysis equation, then it would form that KOH plus that H plus. Okay. However, this KOH is a strong base. It cannot exist in an equilibrium. Therefore, this reaction will not occur. Okay. And so at the equivalent point, whenever we have this salt, only that salt pretty much being formed and no other side products, no excess of our KOH, is it is that salt is going to undergo hydrolysis. Only the anion will undergo hydrolysis, and we will form that OH minus in excess. And so our pH at the equivalent point is going to be above 7. You can also remember my metaphor. I explained this in the paper 1a thing, is that if you have strong base, music is really good at a party, and you got some weak acid, nobody's on drugs, the vibes are really good, and your pH or the vibes are above 7. Okay. And so we know that our pH at the equivalence point is going to be above 7. Meanwhile, our second plateau is going to be when we have an excess of KOH, which is a strong base. So our second plateau is going to be like really high. So like from that like 14 to 12 type of region. And I'm going to make that more flat because it's a strong. Meanwhile, this our like acid one is more slanted because it is weak. Okay, so the last part of this is we just need to figure out the volume at the equivalence point. And so for this, we're going to do some stoichiometry. Is we are starting off with 20 centimeters cubed of 0.1 HCN. So we need to figure out how many moles that is. And then that will be equal to the moles of base, because at the equivalence point, moles of acid is equal to moles of base. And then we can figure out from the concentration how much volume that would be. Okay. And so I'm going to put this just kind of like down here on the side. Is we have this 20 centimeters cubed, which is 0.02 decimeters cubed. So our initial moles of acid is going to be 0.02 decimeters cubed times we have 0.1 mole per decimeters cubed. Okay, and so if I put that in my funny little calculator, because I can't do math in my head, 0.02 times 0.1 is 2 times 10 to negative third moles of acid. And so we're going to have the same moles of base. Okay, so if you have 2 times 10 to negative third moles of acid, at the equivalence point, you are going to have, let me just move over here, 2 times 10 to negative third moles of base. And then since you have the concentration of base, like we just ignore this 30 centimeters cubed because it feels like something that you may use. However, because of the fact that that's just how much you have in your burette, you don't have to use all of it, right, to reach the equivalence point. Eventually you will, and that's why that second half is flat at that 12 to 4. But at the equivalence point, that's what we're calculating, right? And so we have 2 times 10 to the negative third moles of base, and we have 0.2 concentration. Then we are going to divide by that because we want our moles to cancel out to get decimeters cubed. Okay, so if we have 2 times 10 to the negative third divided by 0.2, that gives us that our decimeters cubed of base that we need to neutralize. So at our equivalence point, it's going to be 0.01 decimeters cubed. However, our axes have centimeters cubed, and so we're going to actually just move that decimal place 3 over to the right. And so it's going to be 1, 2, 3. So that's going to be 10 centimeters cubed. Okay, so now we know that our equivalence point is going to be above 7. So we're going to make it kind of that above 7 happening here. And then we're just going to connect our lines. Okay, and so that should be all of the parts of the pH curve. We're going to make that part extend. Okay, and so that's going to be our sketch. In terms of this is where also we should look at the mark scheme. Not like the mark scheme, but the number of marks. The number of marks here is 3. And so for pH curves, it tends to be first plateau, second plateau, as well as the equivalent point, like the volume and the pH. So that's kind of makes sense. For part 5, it says to deduce the point in which the solution would only contain KCN. So that is our salt, and where it would just contain that. And so, like I said, this is essentially like a titration where you have, this is our terrible burette, is you have essentially your base in here, acid in here. So you just have acid first. You keep adding base. Whenever you just have your salt and nothing else, that is at the equivalence point, right? That's why we did those hydrolysis calculations. That why the pH corresponds to that. Okay, and so we're gonna just go salt. Okay, because after this equivalence point, that's why we have that second plateau, is because we don't just have the salt, we have salt and excess base because you keep adding more KOH after that point. Okay. This last part, this part 6, is to calculate the temperature rise of the solution when 30 centimeters cubed of 0.2 is mixed with 30 centimeters cubed of 0.1 acid to use the enthalpy of neutralization in sections 1 and 2 of the data booklet. It was at this point in time that I realized while I was taking the exam that actually the equation of enthalpy is negative Q divided by N is in your data booklet. And I was kind of, that was wild. But anyways, so the equations we want to use here, or we want to use is Q is equal to MC, change in T, as well as our equation of delta H is equal to the negative Q divided by N. We're just going to go ahead and combine these ahead of time. And so we can see that this is delta H is N is equal to the negative MC change in T. And so then we can solve for the change in temperature being equal to the enthalpy moles negative MC. Okay. And so at this point, we just need to figure out which part is which. It doesn't have any like units for temperature rise. So it could be Kelvin or Celsius. I mean, they would be equal equivalent in either way. We want to make sure that our units cancel out in our stuff. So we're going to use the fact of, for our enthalpy, it is given to us as negative 13.3 kilojoules per mole. However, our data booklet, or what's it called? C, our I forgot what it's called, the C, specific heat, there you go, of water is 4.18, and it's joules, grams to the negative first, Kelvin to the negative first. And so since it's in joules, we want our enthalpy to also be in joules. Okay, and so we're going to go ahead and just move that decimal point 3 places over. So that's going to give us negative 13,300. And we're going to put joules, mole to the negative first. Meanwhile, our number of N is going to be, you can do either one, I believe, is that our, because the N is going to be based on the number of moles of your limiting reagent. Okay, so you have to calculate the number of both. So for our KOH, is we have 0.03 decimeters cubed for our 30 centimeters cubed. And because we have a concentration of 0.2, mole decimeters cubed, is that gives us that of our KOH, we have 6 times 10 to the negative third moles. We don't use that number. We have to calculate the other one first, and whichever one is smaller, that's the one we use. So HCN is we have 0.2 decimeters cubed because of that 20 centimeters cubed, and our concentration is 0.1. And so that gives us that we have 2 times 10 to the negative thirds mole of HCN. Since that one's smaller, that's the one we're going to use. So we're going to use 2 times 10 to the negative third mole there. Okay. And now we're going to divide by our mass. And so for our mass, we need to take advantage of the fact that we have to assume for all of these calculations that the specific heat capacity of water is the same as our solutions, as well as the fact that the density of water is the same for our solutions. That's a major assumption we make in all these calculations. So however many centimeters cubes we have of solution is how many grams of solution we have. Okay, and so we have, and it's our total mass. And so we have 20 centimeters cubed and then 30. And so total, we have 50 centimeters cubes of solution. The density of water is 1 gram per centimeter cubed. So it's a 1-to-1 ratio from centimeters cubed to grams. Okay, so that means that we have 50 grams of solution. Okay, and it's negative MC, so we're going to put negative there. Don't want to lose that negative. And then we have this specific heat capacity of water, which is 4.18 grams to the negative first, joule, and then Kelvin to the negative first. Okay. And so whenever you put this in your calculator, you get that the change in temperature ends up being 0.127 Kelvin, which is the correct answer. It looks really small, and I doubted myself here too, but it's not. We can also just verify that our units canceled out correctly in our expression as well, just to check our own work. So our moles canceled out, our grams canceled out, our joules canceled out, giving us that Kelvin up in the denominator, in the numerator, because it's Kelvin to the negative first in the denominator. Okay, and so that also helps reinforce that we're pretty sure that our calculations are right. Okay, and I also did this. I actually, in my own thing, is I actually went backwards as given this change in t with all the other numbers. Is I also worked forwards to calculate the delta H as well, just to make sure that it was right. And that also works because I was really paranoid. I was like 0.127, that's so small. So I also went forwards essentially, just to check my work as well. But yeah, it was right. That is the right answer. And so that is the one extra 1A and B marks. And so in the next video, we'll go over sections C and D.